Okay, so now we're going to do this. We're going to take the total mass, total force, net force. Okay? Net force is this, total mass is this, right? Net torque is this, magnitude of this, right? And it's all times the k vector. So the magnitude, you just ignore the negative sign and get rid of the k, okay? Because the negative sign doesn't matter if you're going to do the magnitude. Okay? So we have this, right? Now somebody objected, but there's a g on something. Well, there's a g on this. There's no g on this, right? But there's a g on this too. So you have the g in the numerator, denominator goes away, so I didn't write it down. Okay? And generally, when you calculate what we're doing, which is actually finding the center of mass, you don't worry about g because it goes away in the end. So you just treat the masses as though they're forces. I didn't want to do that because that confuses people. But now that you see that all the g's go away in the end, when you see your book doing it, if you ever open your book, or when you see it done in an engineering text, because it's usually done without the g, okay? And there are good reasons for that, but I decided to do it. It's a horizontal thing with g, okay? Okay, so anyhow, we'll see why that works. But anyhow, how do you simplify this? Well, let me write it out. M1 okay, it's this. But what happened to all the L over 2's? And I got right in 3s here. I wrote an L over 3 there accidentally. But I got all these L over 2's, right? Well, it looks like it's just minus L over 2 times M1 plus M2 plus M3 over M1 plus M2 plus M3. And I wrote a 3 again, but it's L over 2, obviously. Okay? That makes sense? What's this equal to? Equal to this. Okay? Now, I'm going to ask you to verify it because it's very easy, but you need to do it to understand and bring this around to a picture of what we mean by center of mass. There are easier ways to look at it, but they're a little bit glib. Okay? Or maybe this is a little bit glib, but a combination of that and overly complicated. I don't know. But this is the way I'm doing it, okay? You can see how your book does it. If you do this for the torques around the left end, okay? The torque divided by F net comes out to be M1x1 plus M2x2 plus M3x3 divided by M1 plus M2 plus M3. Now, is there a similarity, and are there similarities and differences between this and this? Anybody see it? Pretty obvious. Give you a hint. Do you see this expression anywhere here?
Yeah, it just doesn't have.
Okay, so that'd be a similarity, right?
Yeah.
Now, maybe you didn't understand where I was pointing, but I'm sure everybody saw that. Okay, well, that's worth noting, okay? So what's the difference between this expression and this expression?
It doesn't have minus L2.
Yeah, well, what's the significance of L over 2?
That's a new fulcrum.
Again?
That's the total radius of the radius of the beam.
Well, it's half the length of the beam, but what's that have to do with?
It shows where the fulcrum is.
I'm sorry?
Shows where the fulcrum is. Shows where the fulcrum is.
Well, that's where the fulcrum is, right?
Yeah.
But even more significantly, if you think in terms of like shifting and stretching transformations, because this is totally analogous, matter of fact, it's kind of equivalent, you've shifted the fulcrum a distance L over 2 to the right, which means that your torque, well, I mean, the torque over net force is reduced by that. When you shift the fulcrum to the right, you reduce the torque, or you change the torque. Maybe the torque was already negative, maybe you got bigger, okay? So wherever I put, so I'm going to assert this. So it's kind of a big deal. If the fulcrum is at position oh man, I need notation again, and I hadn't thought through what I use for notation. So I'm going to just use x tilde, okay? And I'm going to ask you to prove this. It's real easy. You just replace L over 2 by x tilde, and you get x tilde. Can you see that algebraically? And did you see why you'd replace L over 2 by x tilde? Well, yeah, that's what's going to give you your R vectors if the fulcrum is at x tilde, right? Okay? Okay, so here's your big deal. For what value of x tilde is the torque 0? This is the torque. How would you determine the value of x tilde that makes this 0?
If x is equal to, or if x tilde is equal to the other expression.
Uh-oh, I said torque. Should be torque over F net.
Oh. Well, we'll know it to be 0 if and only if m of x1 plus m2 of x2 plus m2 of x3 over m1 plus m2 plus m3 is equivalent to the fulcrum.
So we could just write an equation, set this equal to 0 and solve for x tilde, right? Well,
Is that first expression the sum of mass?
yep.
So at the center of mass.
But now you know why it's the center of mass instead of memorizing a silly formula. Okay?
So at the center of mass is at the fault, there's no torque.
Real easy to screw up these formulas.
Because it's just bends.
Once you can get it to 0.
Okay? Well, F net isn't 0, so this means the torque is also 0, right? Okay, F net's not 0, so for this x tilde, the torque is 0. And we define this to be the center of mass. Why do we call it the center of mass? Well, let's see. So, and now we'll say x center of mass equals, and it just generally sum of mi xi over the sum of mi. Which is also equal to the expression you used in calculus, in calculating centers of mass, if you calculated centers of mass in calculus. And if you didn't, go get any calculus book that's worth having been written. I've never seen one that didn't do center of mass. Okay? If there is one, it probably is not worth having been written, or it's so theoretical that it supersedes anything else. Okay? Okay, so anyhow, this is what? This is the integral of rho x dx over the integral of rho dx. This is the torque. This is the mass. Okay? And then you generalize it to three-dimensional objects and read your calculus book. The idea is very simple.